Welcome to all. Myself Dr. Ditiranjan Patnaik. I am working as an assistant professor in GL Bajaj Institute of Technology and Management, Greater Noida. Today we will see about the optimum filter. So, in digital communication we have already studied about various things in the previous lectures like scrambler, pulse shaping techniques, different types of modulation techniques, and we have already calculated the probability of errors. So, here we will see how the filter is playing a major role to detect the signal from a noisy environment. So, to detect the signal from a noisy environment, we are using the optimum filter in case of our digital communication system. So, before that we have to first see what is a filter. A filter is a system, filter is nothing but a system that is designed to process signal into those we desire. So, filter is nothing but this is a filter, some signal is going, signal I mean some information plus something noise, so something is going, and in the output we require the desired output. Generally the signal information is desired and the noise is undesired part. So, in the filter the noise is your suppressing in the filter, and only the desired output is just coming as a output. So, the purpose of using filter can be various. Why we are using the filters? To extract a desired signal from noisy data. That is the main role of the one of the main role of the filter. Similarly, to transform signals. So, if we want to transform the signal, we use the filters. Then to suppress noise, this is also one of the purpose of the filter. Next, to separate two signals that are mixed in one measurement. So, here we can see the signal plus noise. So, we can separate the these two signals, or signal 1 plus signal 2 also we can separate these two signals using also in using filter. So, an optimum filter is such a filter used for acquiring a best estimate of desired signal from noisy environment. So, here you can see the word estimate, okay, and that is best estimate. So, we can only estimate the signal, we can't get the exact signal from the noisy environment. So, here we are using a best estimation techniques, so that we can get the signal best signal from the noisy environment. So, it is different from the classic filter like low pass filter, high pass filter and band pass filter, these are the classic filters. So, optimal filters are optimum, these are optimum because they are designed based on optimization theory. So, optimization theory either we have already read in mathematics that we are either getting some signal like maximum of something or minimum of something, then at that time we are using optimization techniques or optimization theory. So, optimal filter this filter uses the optimization theory to minimize the mean square error. So, this optimal filter is mainly used for used to minimize the mean square error between the processed signal and the desired signal. That is the difference between the processed signal and desired signal. It will come like come as a error, and that error should be minimized, or equivalently provides the best estimate of desired signal from a measured noisy signal. Okay. So, these are the goals. So, to find probability of error, this is the filter in this section we will find the probability of error, and we will also find the signal to noise ratio, because this signal to noise ratio is a very important role. We have already read about the signal to noise ratio, that is SNR. Whatever we are calculating, we want to show that okay, this system is better, this system is worse according to one major term, that is SNR, plays a very important role. So, we are calculating the SNR also. So, let us say, let the received signal be in a binary format, okay, assuming polar NRZ format. Okay. So, to represent binary ones and zeros, we have already studied about this line coding techniques. So, for binary 1, that is our signal x1 t equal plus a, for 0 it is minus a. Hence, the input signal x of t will be either x1 t or x2 t, that is either 1 or 0, depending upon the polarity of the NRZ format. Okay. So, the noise, now we are considering the noise, that is not the only signal is available, because in the channel there is a noise, in the device there is also a chance of adding noise. So, the noise n of t, that is we have Gaussian, that noise follows the Gaussian distribution with 0 mean. So, is added, the noise is added to the signal x of t in the transmission channel. So, your signal is now it is going like x of t plus n of t. Hence, input of the optimum filter or optimum receiver is x of t plus n of t. So, the input to the optimum filter, that is the signal, either you have x1 t or x2 t, that is your signal is not exactly x1 t or not exactly x of t, it is your x of t plus n of t. So, the optimum filter will filter the input signal, and it gives as a y of t. Okay. And that y of t in digital communication, we will find out the sampled version of the y of t, which is sampling at the capital T instant. Okay. So, this y of t will be like y of capital T. So, what is your y of capital T? Y of capital T equal to your x naught 1 t of t plus your, this is your y of t equal to your how much, x of t plus it will like n of t, the x of t, you can say that x of t may be your x naught 1 t or x naught 2 t. Okay. So, y of t is your, actually this one is your x of t, x naught 1 of t plus n of t. Okay. Similarly, x naught 2 of t plus n of t. Okay. So, your y of t may be x naught 1 or may be x naught 2. Hence, in the absence of the noise, the aforementioned distances are considered. So, next we will see what is happening. So, we have now x naught 1 t plus n of t. I will consider this x naught 1 of t plus n of t equal to x 1 t if x 1 t if it closes to x 1 t. If x naught 2 t plus n of t, I will consider x 2 of t if this sum is close to x 2 of t. Okay. So, if you can see that I have elaborated also in these points. If noise is present, then x 1 of t is selected. If noise is present, x 1 t is selected if y of t is close to x naught 1 t. If y of t is close to x naught 1 t, then x naught of 2 t, then y of t is considered as x 1 t, and x 2 of t is selected, y of t is your x 2 of t, if it is closer to x naught 2 t, then x naught 1 t. I have already told in this section. Hence, decision boundary will be the middle of the x naught 1 t and x naught 2 t. Okay. So, the decision boundary is your x naught 1 t plus x 2 naught 2 t divided by 2. Okay. Let us this is x naught 1 t, this is x naught 2 t, this is the your middle point, this is which is nothing but the, if this point before this point it will selected as x naught 2 of t, after this point it will selected as x naught 1 of t. So, this is your decision boundary. Now, we will calculate the probability of error for the optimum filter. So, here in the noise n of t is considered as Gaussian noise. Okay. This is the main one of the important distribution. So, in naturally all distributions are following the Gaussian distribution. So, here we are considering this noise follows a Gaussian noise. Suppose x2 of t was transmitted, but we are getting x naught of 1 t greater than x2 naught of t. Okay. So, if n of t is positive and larger in magnitude compared to the x threshold, okay, we have already x threshold this much minus x naught 2 of t, then this situation, in this situation the incorrect decision will be taken, therefore, the error will be generated. Okay. Again I want to tell that suppose x2 of t was transmitted, but at the receiver x naught 1 of t greater than x2 x naught 2 of t, then it will what will select x1 of t. So, but we have transmitted x2 of t. So, your noise, this is your noise, that is nothing but x naught of 2 of t, this t plus n of t, that is greater than your x threshold. So, your n of t is greater than or equal to xts minus x2 of t. Okay. So, x threshold is this much, this is this much, and if that is n of t is greater than x naught 1 of t minus x naught of 2 of t divided by 2. So, hence what is the probability of error? Probability of error is nothing but this is the error. This is the error. Now, in the probabilistic approach, we can proceed like probability of noise greater than x threshold minus x naught 2 t. So, I can write x, I have calculated this much like this one. Okay. Now, probability of n of t greater than or equal to x 01 t minus x 02 t divided 2. Therefore, the probability density, now we will consider first what is the probability of noise. The noise follows the your probability Gaussian distribution. So, this is the Gaussian distribution with this is your 1 by sigma root 2 pi e to the power minus n square t by 2 sigma square, because your noise has a 0 mean and your standard deviation is sigma. So, I can write the PDF of noise is this much, hence n of t is a random process with sigma with the standard deviation and the function has 0 mean. Okay. Hence, to evaluate the probability of error, we must integrate the PDF. So, I have to integrate the your PDF that would be from this threshold point to infinite, because I am getting instead of x naught 2 t, I am getting x naught 1 of t. So, I have to integrate this in the region x naught 1 t and x naught 2 t. Okay. So, how to calculate this? So, x naught 1 of 2 t minus x naught of 2 t divided by 2, this point. How this point is recovered? This is your like this is your Gaussian distribution, this is your x naught 1 of t minus x naught 2 of t divided by 2. I have to find this region. So, this after this is a infinite, this is the, I have to find out this area, because this is the error probability of error area. So, I have to find out the probability of error by integrating the PDF. So, this is the limits, and this is the PDF, and after that this PDF, I know this PDF is nothing but this one, and this is dn of t. So, your P of E that is probability of error equal to 1 by sigma root 2 pi e to the power minus n squared of t divided 2 sigma square multiplied by d n of t. Now, I have to solve this integration. So, let n square t divided by 2 sigma square equal to y square Then from this I can get y as a n of t divided by root 2 sigma, and dy equal to d n of t divided by root 2 sigma, and d of n of d n of t equal to your root 2 sigma dy. Now I got this d n t in terms of y, okay, I mean in terms of dy, and I have already changed this one to y square. So I have to change the limits. How I can get the limits? As n of t, your n of t tends to infinite, your y tends to infinite. Why? Because this is the relation. Okay, this is the relation y and n of t. If n of t tends to x naught 1 t minus x 2 naught t divided by 2, then y tends to how much? This much. This is n of t, this much divided by root 2 sigma. This is 2 times root 2 sigma. Okay. Now your probability of error is, this is the instead of this limit is this one, this is the limit, and this is the everything you want to write here. So your probability of error equal to, now after simplifying this much, it comes like this, and now I will multiply one in the denominator, I will multiply numerator in the multiply 2, and I will multiply the divided 2 in the denominator. After that it will look like your why I am doing like this, because I know ERFC is nothing but a 2 by root pi integration x to infinite e to the minus y square dy. See, this is the, this one is same, this is instead of x I have this much, but I don't have 2 by root pi. So to make this like this equation, I have divided by 2 and multiplied by 2. Okay. So at last I will get half ERFC of x naught 1 t minus x 2 naught t divided by 2 root 2 sigma, because your x is nothing but this much, this is the x. So you know that ERFC function is a decreasing function. So if your this difference increases, then your ERFC function would decrease, because your 2 root 2 is constant, sigma is also your constant, because only variable is your this much, I mean x naught 1 t minus x naught 2 t is only the variable. So if this would increase, then ERFC function will decrease, and hence the probability of error would decrease. Okay. So now we will find out the SNR and transfer function of the optimum filter. So let x naught 1 of t minus x naught 2 of t equal to s of t. This is generally we have x naught 1 t minus x naught 2 of t. So this is s of t, then probability of error is nothing but half ARFC of s of t divided by 2 root 2 sigma. Okay, this is 2 root 2 sigma s of t. So I can write s of t. Okay, I can write half ERFC. All things if I will take inside the root, okay, square root, then it would be s square t divided by 8 sigma square. So your SNR, that gamma square equal to SNR, is nothing but the signal power divided by noise power. So I can write this ERFC of, in general we have half ERFC of SNR like this, root SNR. So SNR is your s square t divided by 8 sigma square, that is nothing but your signal amplitude power divided by noise power. Okay. So now we will find out the transfer function, that is your see, this is for transfer function, this is the filter h of f whose transfer function is, this is SIT, the input signal power spectral density. Similarly your output signal SI S naught t in frequency domain, this much, this is the frequency domain. So in frequency domain I can write S naught of f equal to SIF multiplied by h of f, and I can write S naught t equal to using the inverse Fourier transform, I can write S naught f is given and e to the j 2 pi ft df. So to find out the gamma square, we have to find out the transformation function of S of t, okay, because gamma square consists of S square of t, okay. So, this transfer function is basically a optimum filter, that S of t is nothing but your optimum filter. So, let Si of t is the input signal and S naught t is the output signal, okay. So, S naught f equal to your in frequency domain, this is like multiplication of in frequency domain input and the transfer function. This S of f is the optimum filter transfer function, okay. So, S naught t equal to how much? I have already told you, that is this is the using a inverse Fourier transform. So, S naught t equal to your S naught f is nothing but the SIF multiplied by H of f. Now, S naught to S naught t square equal to minus infinity to infinite SIF HF, this is the square, just square I have done, this is the modulus square, okay. So, now I can expand the noise like, so this is the input PST of noise is your GNF, output PST of noise is not, let us say GN naught of F. The input and output PST, power spectral density, are related as GN naught F equal to output power spectral density equal to input power spectral density multiplied by H square of F. This is a power, okay, that is power spectral density. So, this is the general model. Now, we will write the PST in the terms of power, okay. This is because we will need this for calculating the noise power. So, the variance of Gaussian noise is nothing but the noise power, this is the main important point. Variance is nothing but your the power, that is noise power. The relation between the noise power and the PST are related as the noise power is nothing but the integration of the power spectral density, okay. So, sigma square equal to the integration of power spectral density. So, power spectral density I know the power spectral density is H square F into GNF, okay, H square F into GNF. So, this is H square F GNF. So, gamma square I have sigma, I have already found out the S square of t, now I find out sigma square. So, this is the S square t nothing but the, this is the this one and this is the your sigma square part. So, using Schwarz inequality, if I have x of f and y of integration whole square divided by x of f square, it would be limited as bounded by integration of y of f df whole square. So, here our x of f, in this case our x of f is your h of f in root gn of f, y of f is equal to s of f divided by root gn of f multiplied by e to the power j 2 pi f t. So, I can write that gamma square is less than equal to minus infinite to infinite your 1 by root GNF, okay, 1 by root GNF multiply SIF into e to the j 2 pi f t square df, okay. So, I can see that for equal sign this is less than, but for equal sign I have to equal some constant, I have to equate some constant k, x of f equal to k times y star f, with k is arbitrary constant here, this is the conjugate. So, h of f multiplied by root GNF equal to k times your, this is your y of f. So, y of f is nothing but your s of f divided by root GNF multiplied by e to the j 2 pi f t, but y star that is e to the minus j 2 pi f t. So, h of f equal to how much? This will be the result of h of f, okay. So, this is the main we have calculated the transfer function of the optimum filter. Before that we have calculated the this is the SNR. So, we have calculated the SNR part here, this is the S square t divided by 8 sigma square, and now we have calculated the S naught f h of f from this optimum filter. So, this is the step, this is the S square t we have calculated, this is the sigma square we have calculated, now gamma square equal to S square t divided by sigma square, and using the Schwarz inequality we have found out this much of this is the h of f, this much of the we can say the transfer function. So, in the next lecture we will see these are the references from where I have taken these points, and in the next lecture we will see the matched filter where we can say that the power spectral density, noise power spectral density is your white Gaussian noise, or noise is your noise follows the white Gaussian noise. So, thank you very much.